I have here a bullet hell demo. The source code is available on GitHub, but the focus of what this video is on is going to be about a performance comparison between three approaches: normal game objects, game objects with pooling, and also a DOD style approach. This will be one video in a series of videos that I plan to cover different types of games with DOD style systems and show you how to get the real performance gains out of it. I'm going to start at a high level, then down to certain lines of code, why the sequence of the code even matters in the performance. Additionally, there are some hacks that I take to get even more performance out of it because of the fact that we're operating at a lower level memory and we have more control over it. Right now, we're looking at level 1 game objects and the normal setup of it. That means that every time that a cannon fires a cannonball, it will instantiate a prefab. And that prefab will continue moving forward until it collides with a wall where it will destroy the prefab. In this case, we're seeing about 1,500 to 1,600 objects at any point in time. And our CPU average time for processing this data is about 13.5 milliseconds. Our GPU average is about 7.5 milliseconds. Having to create and destroy memory repeatedly is expensive. So let's find faster ways of dealing with this. In level 2, we have game objects with pooling. This is going to give us a slight improvement. The GPU tends to stay about the same for the expense because we're drawing the same number of objects in the same style. That hasn't changed. But the CPU average is remaining pretty close. However, also to note is that we have gone a little bit higher in the number of objects. We try to stay about the same, but we don't have complete control. It's just the timing of when shots are being fired, and the different systems are really close to each other, but there is a slight random variation in how they get sent out. We're still seeing a subtle improvement since we have a higher count. What the pool does differently is the pool takes the shot, and the first time that we ask for one and it doesn't exist, it will instantiate it, just like normal. Once that gets destroyed, instead of being destroyed, it gets passed back to the pool. And the pool then, any time that something requests for it, will grab an instance from its own pool. That means it doesn't need to destroy the memory and instantiate new memory. All the ball prefabs already exist. And so we get a subtle performance boost. Now let's move on to the DOD form of this. That's where we're using data-oriented design. We're using structs inside of them, and we control the memory order. So we end up getting a much faster speed. We're also drawing them in an instanced format, which makes it happen faster. In the other ones, we were seeing stable about 7.5 milliseconds. Now we're at 5 milliseconds pretty stably. But look at the difference for the CPU times. We were looking at over 13 milliseconds before, and now we're looking at under 9 milliseconds. That is a significant boost in performance. So how do we do this? With the game paused, here's a brief overview of where things are being stored. First off, there are 4 scenes. We have demo, and then we have L1, L2, and L3. L1 through L3 basically look the same. They are the exact same structure, but I've changed out the code and the prefabs that they're using. So same shots, same information, but different management of the data inside it. And each level has its own set of scripts. So L1 has its own set up here, L2 has another set, and L3 has another set. They are completely separated on code, except for some of the common demo scripts. Now, the demo scene and the demo scripts are maintaining performance information, and there are some key benefits to what we're doing inside of them that I might show in separate videos, and a few pieces of it I'll try to show now. Let's take one quick look over at the demo. And when I take a look at this, there's very little code in here. It has the canvas, and the canvas just stores a demo, which is now going to be statically available and maintained every time we change scenes, and also the demo results UI, which is what is drawing all the information up to it. I haven't actually tested it on client machines to see if the where I'm getting the 2 pieces of information for performance, the GPU and CPU times, are available outside of the editor. One more general call out that you might want to check out is the curve texture util. Originally, when I was displaying the performance information, I was using an animation curve to do it. And so I had some code up here that would take that animation curve and generate a graph so we could see the performance as it moved along. However, this was slow. A lot of that had to do with the fact that an animation curve doesn't work well with looping data, and so I had to modify its structure. And so instead of using animation curves to store performance information, I'm now using a ring buffer, which is basically a looping array of data. If you have the idea of recording a camera and you're recording that to a looping set of memory, it means that by the time you reach the end, it's going to go back to the beginning. I'm not planning on covering the details of how the ring buffer works inside of here, but I may cover that in another video, especially if anyone asks about it. Now, let's start taking a look at level 1. So every single one of these levels has a demo record for call, basically a script that we're going to call the demo and tell it to start recording under a heading, in this case L1 GameObjects Normal. Now what that means is all the stats that are being recorded will go under this heading. It will be associated with this heading and display as it in the UI. I'm also going to briefly cover turret sweep here. Turret sweep is fairly important because of the fact that it is the same in every single one of these. There is a slight difference in DOD, and we'll get to that. It's a performance hack that I added. The key to understand is that inside of this, it has a minimum and a maximum angle. These are the angles that it moves. It can along the y-axis. Let me show you that in the actual scene. In level 1, I'm going to expand out one of the cannons. I'll double click on it so it brings focus. Let's get a better angle. And we can see the minimum and maximum angle. When I move it, we get to see a little green line that indicates where that actually is located. And we have the same thing for the red line, which is the maximum angle. And that means that when this is rotating around along the y-axis, it's going to spin between those 2 points. The math that we use is fairly simple. We're using a mathf ping pong to go from 0 to 1 to 0 as the time moves. And then we get our angle by lerping between the minimum and maximum angle according to the time. Now, the turret doesn't actually cover firing, so let's go over to the firing script. We have here 3 key points of information. The frequency, which is how often we fire, the prefab, which is the object we're going to fire, and then finally the firing point, which is where we'll fire it from. During the update, we keep taking the timer and adding the delta time. Once we exceed or meet the frequency, we're just going to instantiate that prefab. We're going to do that at its position for the firing point and at the same matching rotation. This instantiated the shot, but then we still have the shot itself. Here, the shot is basically got a speed, and then during the update, we take its position and we add the transform's forward direction times its speed and delta time. That keeps the object moving along a constant velocity. And finally, on trigger enter, which means that we're hitting another object, we do have the physics tuned so that the colliders ignore other cannonballs. I do want to emphasize how useful it is inside of Unity to be able to just create a mono behavior with a shot that destroys itself, it manages itself. This whole script is self-contained. It's very comfortable, but we're here for performance. So this brings us to level 2 game objects with pooling. Everything in here does the same thing. Turret sweeps is exactly the same code. There was no modification, but I do have a separate class structure just so that we understand that they are separate. Now, there is a difference inside of firing and shot. So let's go into those. In firing, instead of instantiating the prefab, passing in the position and rotation, we instead get a shot from the pool. I'll go into the code in that in a minute. And then after we get that, we can't instantiate it with the position and rotation. So we have to set its position and rotation. We have to establish what state it should be at now. The next change is in shot. So shot, instead of destroying the object when we collide with another object, it is going to return the shot to the shot pool. So let's go take a look at the shot pool now. Here's those 2 functions we were using. There's a lot of videos that go into more depth and detail on object pools. So now this brings us to where we were seeing the most significant performance increases, and that's going to be from our bullet DOD, data-oriented design. And so I'll start diving into the code for it. I want you to get away from the concept that every single object has to have its own scripts and components managing it. It has to have its own instance in memory, and it has to have a renderer and its collider built into the single object that's there. It's very comfortable to be able to build with that inside of Unity, but those are all classes and they are expensive in memory. I'll get to exact details why in just a minute. We're going to be managing this all with a SHOT system that actually stores the data inside of simple arrays of structs. The SHOTs don't manage themselves like they used to. Instead, we have a system to manage the SHOTs. It's nice. It's comfortable to have those benefits of game objects where we can just create the game object, throw the components on it, and suddenly it behaves and acts like we want to, and we don't have to think about it as much. But that luxury comes with a cost. So we want to get rid of some of those costs, and to do it, that means we actually have to dive in and do some extra work to replace it. Let's start out by taking a good look at the firing system. Firing system is still largely the same. We have a frequency, we have a prefab. Hey, we don't even use the prefab anymore. I just didn't get rid of it. Yeah, we do need the firing point, but we don't need the prefab. Whatever. Instead of getting a shot that is now just going to sit out in game object memory, we're going to use our shot system and have it add a shot, which means it's got its own collection of memory that's going to organize it so it can run through it faster in a way similar to that ECS does. Lifetime is basically a hack that allows us to destroy the object after a particular amount of time. And that allows us to skip physics checks. And I'll get into how that works and why we're able to avoid physics checks in this case and gain the extra performance levels. But we can't cover it yet until we've explained a little bit more into what's happening here. Let's dive into our shot system in more detail now. First off, there is no prefab. It doesn't instantiate one. Instead, we have a mesh and a material. And then we also have a collection of shot transforms, these matrix 4x4s that tell it where to draw this. Now, if you haven't seen the video, there is a separate video that goes on before this one that dives farther into detail about how this mesh instance system works. And I'm only going to cover it lightly here. During the update, we call graphics.draw mesh instanced. We pass in the mesh we want, we pass in the material we want, we pass in an array of matrix 4x4s, which is basically our transform. And finally, we pass in a count of how many of those in that array we're going to draw. And that is able to handle drawing much faster than individual renderers on individual game objects. Now, there are 3 arrays inside of here, and we initialize them all at capacity. These are, so in this case, we have 1024 for our capacity, and technically I have that bumped up to 3000. And we have a count of 0. That means that we instantiate our array at the full capacity, but we're not using it all. We're using 0 to begin with. And as we add shots, we will increase that capacity. One of the things I want to call out is that when we do exceed the capacity, this one does not create more shots. When we're talking about a game like StarCraft, where they have a limit of 200 units that you could have for any player in a match, at the beginning of the match, they can allot as much memory as they need for the player types that are coming into the game. And no matter how many of these get destroyed or created during the gameplay, the memory is already there. This gives us predictable performance. During AddShot, we get a position, we get a rotation, we get a lifetime. We take that information and we store it into an existing array element. We don't have to construct new memory. We don't get rid of memory. We don't restructure our arrays. We just take existing spaces in the current arrays. So for this one, I add a shot. I also add a transform. And to get the transform, its position, I'm just using matrix4x4.trs. That lets me pass in everything for the transform, the position, the rotation, and the scale. So in the update, we effectively have 3 sections that are happening. A lot of the performance happens right here. The first is that we're going to update shot positions and lifetimes and mark for removal. That mark for removal means that we're not actually going to modify the arrays here, not the structure of them. We will replace values that are stored inside it, but we're not going to delete records from it. So instead, we're just going to mark records to be deleted at a later time. And this is going to be important for performance, and I'll explain the exact reason why. Now, the second thing it's going to do is it's going to go through all of those replacement indexes, and it'll go get rid of them at that point. The third thing it does is it's going to draw it all using the graphics.draw mesh instanced. Now, let's dive into the first loop. Shots.time remaining. Basically, this is a countdown. How much time is remaining, and we keep subtracting from that. Once that gets to 0 or below, we go to our replacement indexes and we add a new record. We are increasing the replace index count with the plus plus, but before that happens, we are setting the current one to whatever our I is. Now, this is an array of int 16s, and one of the benefits of that is that means a single cache line of 64 bytes can hold 32 of these at the same time. We are storing a record saying that we should remove this. We're not actually removing it here. I'll get into why in a minute. Down below, let's say that we still had time remaining. In this case, we're going to get our position from the shot transform. So we go out to the shot transform array and we say, get us column 3. That effectively is a vector 4, but we're just going to cast it to a vector 3. And then we're going to add our velocity to the position. And then we're going to put that data back in the shot transform. And we go through every single shot and update their time remaining, and we update their position based on velocity. Assuming that we needed to remove some of these, we've been incrementing our count of these. We have several of them queued up maybe. We get over to here. This is where we go through all the items from 0 to the replacement index count. We get the replace index so that we can use it, and then we decrease the count. Now, if it was the last one and we just said, hey, we needed to delete the record of the last one, then we don't need to do anything with the data. We can skip moving around data here. So if we have 100 items, we deleted the last one in it, so we now have 99 items. We just reduce the count to 99, and now it'll only draw 99 of those if it was not at the end. We're going to do something that ECS does under the hood when it's working with chunks and deletes data from those chunks. When it erases an entity, all it does is mark that one for removal, and then it takes one from the end and copies it over to that point, and then reduces the count of the total numbers in the chunk. Because we don't actually care about where it is in the index. When we're going through here and we're updating, all we care about is that shot transforms and shots line up. So if we're going to remove one, we're actually going to do it to both at the same time. We take our shots and whatever index we were going to replace, and we grab the one at the end and copy it over. We do the same thing with shot transform. I could just take this whole section of data right here, actually this piece, and I could go up to the top and I could say, hey, instead of doing this there, why don't we just do it here inside of this one? What would be wrong with that? Well, let's first off fix some I's here because it's not replace index anymore. It's just I. Why would it be a bad thing to do it this way? Well, if I just deleted record I and I copied the one from the end back into position I, and now we move to the next one, when do we ever process the shot that was at the end? We don't. That means that we have to do one extra step here. We have to do I minus minus. But what's that going to do? Why would this be such a bad thing right here to have inside of our for statement? As a quick explanation for prefetching, prefetching just wants to take a look at the line of code you're on and say you're asking for some data here. And this data is at position 0. And the next time we loop around and come back to that same line of code, it has a table it's storing that says, what were the last 2 records that you had? And the last record says that, well, it doesn't know anything. The next time you come past, it says, well, your last record was at 0. This time you're coming into it, it's at 64. And the next time you come into it, it's at 128. And by that time, it realizes, hey, for the last 2 times I went through this, and this one, we've been incrementing it by 64 bytes every time. That means I understand I will very likely come around to here again and grab something at byte 192, the offset from whatever array. It's just moving forward by 64 bytes every time. So 64 bytes, 128 bytes, 192 bytes, 256 bytes. It keeps moving forward. But as soon as we throw this I minus minus in there, we went from 64 to 128 to 128. All of a sudden, the whole prefetching idea is gone. It gets thrown out. And so it still happens to have a piece of that memory sitting around, but it's not going to be reading ahead again until it's looped through here 2 more times and finds a pattern again. And if you're replacing every other one, it will never prefetch anything. You will have to pay the RAM cost every single time it has to do this. And so I minus minus is terrible inside of an array. We kill our prefetching capabilities. So it's far better not to have that, but to simply increment this. We do not want to manipulate the I. We don't want to change how the I flows through a for loop. That slows things down. Now that brings me to a separate issue. Let's say over here, we get to this, we're updating the position, and we're grabbing from shot transforms. Shot transforms is the one that takes 64 bytes for every one of these. That's an entire cache line. That's how much data a prefetch cache line can be. But if we ran out of time, we go into replacement indexes, we skip ever interacting with this. The prefetcher looks at the line of the instruction that says to go get it another piece of data. And it says, when we return to this line of code, if we have moved forward the same amount of bytes the last 2 times, we'll prefetch ahead. Our prefetcher will know to start reading ahead. In this case, it will go 0, 64, 128, and then 256. I have not jumped ahead 64 bytes. I've jumped ahead 128 bytes. That means my concept of prefetching is gone. Let's go to the shot transform, and let's get that every single time. So it doesn't matter whether or not we're going to remove the index. We're going to grab our position up here. So every loop, we grab the position. Now, a compiler might intelligently determine around this that we're putting the order in, we can move this stuff around to get a better performance. However, I don't like to leave it to the compiler to know the best potential spot for that. Especially the more complicated something is, the less likely a compiler is going to know that, oh yeah, if I move this piece of data over to here, it will do better. Compilers are good, but the more steps you have in between, the less likely they'll have a chance to understand what on earth you're trying to do with your data. This is a normal spot where I would have taken position and I would have said, hey, why don't we push this down here? We don't need to access this index of the array. We don't need to grab that data every single time. I mean, grabbing data's got to be a little expensive, right? So we skip that step, except that we now ruin the prefetching order, so we actually make its next 2 calls more expensive. Now, there is an alteration to this. Let's say that we were to have a special effect in the game that destroys all the shots at once. A lot of games have like a nuke effect or something like if you get hurt, then all of a sudden all the shots get blasted away. In cases like that, I would recommend that you actually create a special additional function inside of your shot system that says destroy all shots. And you know what that function is? Count equals 0. If we do have reason that a lot of objects will get destroyed in sequence, then yes, in those cases, continuously grabbing these, we are costing additional cache line reads every single loop that we don't need. So yes, we have a nice cadence, a nice performance over our loop, but do we need to loop to that data or could we teleport? If we teleport, it can't predict what our next prefetch step is. But if we move with a nice cadence, it understands we're moving at this rate. It will grab that data that far into the future. 1,000 times in the past, I am sure that I have done this, where if I have an if statement inside of a for loop, that when I need to grab one of the records, if I didn't need to grab it, I would have put that value request into the if statement, that I'm not going to grab it every single time. And I had no idea that that would have impacted the performance. And of course, the last thing is that we draw the mesh. I mentioned before that I'm able to avoid having to run physics checks because I'm using time remaining instead. A simple value that I just decrease every single time. How am I able to do that? How am I able to use time to determine how far off a wall is? I can have a lookup table where I can say if my turret is at this angle, I know that it's going to have to move this far before the shot actually hits something. Let's walk through the code on this because this is a special hack that I did because I'm taking control of my own physics. Let's go to level 3. I'm going to expand out Canon and let's take a look at one. Inside of Canon level 3, it's got distance by Y angle. And technically it's not going to be distance. This isn't distance. It's distance and time added together. Distance by Y angle. Now, if I expand this out, you can see that this is a curve, an animation curve that holds some data inside of here. It holds a bunch of points. The cannon, the way it's firing right now, it's pointed directly at this wall. This is at 0 rotation on the y-axis. So it's looking directly at the wall. Now, as it turns this way, it's going to start pointing at the wall and it'll end at different spots. So you can see its distance over here is going to be a little bit farther. Well, look at this. Here's our distance, which is, let me just click one. I have to hold. We're at 2.8 meters. This right here is 2.8 meters. We saw this where it slowly starts rising away, and that's this first bar. And then suddenly it comes to a spot where it can see farther away, this little sweep right here, between here and here. And so we see this spike where it comes up. And it's again another wall at the same angle, so it'll start at one side and then get a little farther away. And what do we see? Spike where it jumps up, then it moves a little farther away. The angle is a little sharper, it's a little farther. And then suddenly it goes to this wall where it's largely flat. It should change just a little bit, moving away up a little bit as it goes to this side from this side. And that's what we see. Over here, it starts rising up just the tiniest amount. It mostly just looks like it's flat on here. And then suddenly it gets another burst to over to this wall. But now this wall, as it moves across, is going to be starting to get closer to it. So we get over to here, bursts up as it suddenly hits this corner up here, and then it starts moving closer. Here it starts moving closer. And then suddenly it gets to a spike where it's going to go much farther away. So as I scroll up, now we see that this curve is going all the way up into this stuff, and it gets some other junk in here in the background. And so we see these weird spots where it kind of goes up and down off into the distance. I'm re-baking out the data for where this is. Now, if I moved this object, like let's say I moved it over here, I would get a different structure. You can see this structure, what it looks like right now. I'm going to go up to Tools, Firing L3, and Bake Distance Curves, all in Scene. Now this goes through, finds all of the objects, and sets their animation curves. So we start seeing different sets of curves on how we end up moving around that data. Let's go take a look at what Tools Firing L3 actually does in its code. Let's see, that should be up here, Firing L3 Curve Baker. I'm going to click on that one. Again, this is all in the source code. You can check it out too. This is just a shortcut hack to bake in those distances. So the first thing it's going to do is get the shot system. And the reason it gets the shot system is because that has a shot speed. I need to know how fast the shots are going. If I'm going to determine how long a shot can stay alive, I need to know how fast it's moving as well as the distance. The second thing is I go through all the firing L3 objects that I can get. Now, for every single firing, remember this is a firing L3, that's the thing with the animation curve. I'm going to call bake single firing. This passes in the firing L3 and the shot speed. So here's the bake single firing. I need to figure out how wide apart we're going to be checking these. So on the one that I was just looking at, it's got a check angle of 1. If I were to click on another one, this has a check angle of 0.1. Each of these do. This is the only one that has 1. But if I look at the data in here, they're still so densely packed. This seems like more data than I need. I'm going to take a snapshot here, print screen, and let's grab this one. So I've got my original snapshot up here. I'm going to shrink that down so we only see this part of it. I'm going to set this to 10, and let's run this Baker tool again. Tool, firing, bake distance. And look at that. When it's looking every 10 degrees, that's really terrible. We end up with like 36 points on here. And now look at the resolution of these spots compared to here. We're losing a huge amount of data. So obviously 10 is way too small. I'm going to move this data back into here, and let's change this to from 0.1, which it was what we were originally doing, to 1. Let's try that one, and let's go back to Tools, Firing L3, Bake. And now I'm going to move that off of here, and let's bring up the new one. Now compare the data. We're just going through each one of these angles at a specific step interval, whatever we set in our check angle, from 0 to 360 degrees. Now we get our direction, we do a ray cast off in that direction. Remember, this is all just running off of the y-axis. We do a ray cast against our max distance, which I think right now is just set to 5,000. Yep. If we didn't get anything, if it didn't come up with a hit, we just put it at 5,000. So once it gets to that end point, it just destroys itself at 5,000. It should have by then, but just in case, we're still going to destroy the object. But otherwise, we set the hit distance. We take the distance, divide it by shot speed, and that gives us how much time before we hit the wall. Now we add that to our animation curve. We add a keyframe that at this angle, we're going to have this much time to hit. When we are inside of firing L3 and we say, how long is the lifetime? Well, we get our animation curve, distance by Y angle, and we evaluate it based on our Y angle. And that returns to us a lifetime, how long this shot should be alive. That if we are pointed in that direction, then we're going to hit a wall in exactly 2.78 seconds. No physics necessary. Now, obviously, in a bullet hell game, you're going to need physics, but it's going to be so much faster on your performance to have something that run through this array and see if any of these shots hit this player. This means that at runtime, we are not doing any collision checks. We're not doing any ray casts. We're not having to look up memory from many different random places. We have improved our speed here significantly. All right, so DOD is not universal. Use it where your data is dense, sequential in an array of structs. You need to measure before trusting this. This should be burst compatible as well. Please, if you notice something inside of here that's a mistake, call it out in the comments. If there are patterns that you want to see addressed, comment on it. Let me know what types of genres or game patterns that you want to see DOD applied to see if and how it can improve the performance. If you're still here, thank you for watching. If you're looking for ways to support the channel, please like, subscribe, share, follow, and buy me a coffee. I'll talk to you later.